Okay, fine. So Peter asked me to give a talk tonight on model discrepancy. So I'm going to do this in a very informal way. This might be a very short talk, or it might be a bit longer, depending on whether you say, yeah, fine, we'll do that, or whether you say, wait a minute, and raise issues and things we want to discuss. Okay, so model discrepancy. Let me start, I guess, with an example which I find helpful in thinking about this. So I've been looking at computer models for complex systems and how they differ for a very long time. So the first ones I ever looked at, in fact a group of us in Durham University did this. So this was back in about 91, 92, before some of you guys were born. And so we got involved in a problem about matching computer simulators to oil reservoirs. Okay? So you have an oil reservoir and you build a model for it that describes essentially the underground sort of geology, permeabilities, porosities, faults, how the aquifers work, etc. And obviously it has many things that you don't know. So they had the problem that they called history matching. So what Victoria called history matching yesterday was because we I won't say stole, we just thought that's just a good term. So we looked at the problem of how would we history match the reservoir, and we said, well, that's just a general thing we would want to do for any computer model. Now, in the oil industry, history matching refers to using some kind of tweaky, one step at a time optimization to find a single match. And we thought that was a stupid use of such a great term, so we backed it out to mean just finding all the matches. Okay, but the notion of where the term history matching comes from. Okay, so now, almost the first things we were told. Okay, we were told every time you get involved in a problem, there's a massive science that you have to survive and organise. So this was one of the things that they stressed most. Okay, so let's imagine that there is a particular well, and this is time along here, and this is pressure. Okay. So at various time points, historically, at each well, the pressure is measured, okay, and that is an important indicator of what's happening, and being able to predict pressure sort of downstream is an important thing. Okay, so they would have a bunch of observations. Maybe it looks like that. The picture will probably be a bit crappy, never mind. Yeah, okay. So in a history match, I specify the entire geology of the reservoir, I run it across this time, and I look at what the simulator says the pressure would be at each time point. Okay? And history matching, we would like effectively to get the run of our computer simulator basically to hit all those crosses. Yeah, obviously not exactly, because of all the errors and uncertainties, but history matching is getting ones that do that. Okay? So now the key thing they stressed was you could imagine different kind of solutions. Here's one, so this would be, so I choose a particular geology, like a set of parameters, and I run. So here's one run that I can get, and it could look like that. Okay? So it's missed. Yeah. Okay? Here's another one that I could get. Okay, I'm doing a different colour. Let me use this board so it's full splendor. Okay? It could look like that. Yeah. And the key point they stressed was that even though the blue line was closer to each X, they liked the yellow line. Okay? Partly because they said that, in a sense, it's clear where, if I go into the future, okay, it's clear what's going to happen. The yellow line will go along here and it's going to drop it a bit, so it's clear what's happening. But they also said that was because they understood effectively what's going on here. Well, understood is too strong, but it seemed reasonable to them that such a discrepancy should be. Okay? And the reason is the following. Okay? That if you imagine an oil reservoir, it's a physics model, and they solve it on a grid. Okay? So you have a grid, and you have grid blocks. Okay? Now, the wells are in the grid blocks, but certainly at the time, probably still now, effectively, because of the way that the models work, you move the well to the centre of the block. Yeah? Which means that where the well is in the model isn't exactly the same place as where the well is in the reservoir. So if you can think about it, one way of thinking about it is they've kind of messed up time. Because the time it takes for us, if I inject something, the time it takes to get to where the well is and to do something will be a bit wrong, and it will be the same bit wrong. I mean, not exactly the same, because the physics will blur this, but it will be an offset.
Yeah. But why don't they interpolate?
Well,
because if it doesn't fall on the grid, why don't you make it?
Because in fact it's more complicated than that, in the sense that well, we'll talk about that question, yeah. But the things that you can do to make certain things better, which could easily make other things worse, and they're trying to do this for not just this, but for everything. And if you like, timings is a complicated, which things are functions of time being wrong, and there are other things as well. So it's a bit more complicated than I said. But when we come back to it, why don't they interpolate? Effectively, that's what they're doing. What they do is exactly they're saying there's this offset, but they're going to cope with it at the level of the output rather than I mean, when I say that when they predict along here, they will run this along here, dot 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 dot, and then they'll drop it down. It's a form of doing that.
Because with data simulation, weather prediction, they have the observations, not at the grid point, and then you were mentioning
now, weather prediction is a team of people who spent a zillion years who are super trained, have masses of data, and get feedback every day, and if they get it wrong, people are killed them. These are just the guys who just say, oh, we're going to build a model, and we're going to do this. And really, we want to be flying out to somewhere exciting and getting our next contract, but we have to sort of mess about with this model. It's a different world.
Yeah, right?
Yeah, but anyway, I mean, if you think about the example, okay, so the point is firstly that they recognise that the model output will not be the same as what we see. Not just because of observational errors, but because of systematic features. Okay? Secondly, they're not just trying to get the best fit point-wise, they're trying to get some notion of global fit, and effectively what they're saying is, that obviously they didn't use this language at all, that discrepancy, one of the most important features of it is the correlation structure. If there's high discrepancy at one point, most likely there will be a high discrepancy sort of at neighbouring points. Yeah. So there is, so as we think about when we think about bringing any model to the world, all of these are since the starting points that we need to think about. So model discrepancy is effectively understanding the limitations of our model, understanding ways that we can correct them, and we can correct them by modelling better, or we can correct them externally. Okay? And correct is too strong a word. We can make allowance for in some way that we want to talk about. Okay, so
Michael, I mean, then what you're saying, or that they don't really like the model resulting in the yellow line per se. They like it after they've applied a correction.
Yes, no, exactly.
Which makes it a good model.
Yes, yeah. So the notion about what the model is the model now that, or is the model that plus correction? But they weren't making, all they knew, of course, was that they were really should be on top of this, and rightly or wrongly, and of course, I mean, I've made it more simple than it really is, but the principle is there. Yeah.
So in principle, though, the blue line, I'm interested in what's, the blue line, whatever way you look at it, has a low discrepancy.
Yes.
So what's wrong with the blue line is not discrepancy, it's something else.
Well, the blue line, there are two things that they worry about for the blue line. Firstly, see, if I now take time along this way, okay, and they're not sure what the discrepancy is, but I think that the more, they don't really know how to extrapolate, I mean, how effectively to rely on this. Secondly, because they feel that the offset should have some systematic pattern, they're worried that they've made, I mean, there's two ways that you can get a match. you get a match because in some sense you've got the physics and the geology right, or you've got a box of curves and you found a curve that can fit. Yeah?
Yeah.
And if it's just a curve that fits right up to about that point, you know, if you just do, if I'm trying to take a series of points and I just have a box of curves and I find one that fits very well within the series, I have no great confidence it will extrapolate well.
Mm.
Yeah.
So what would you, well, that's what, to me, with my background in statistics, which isn't great, I would call that overfitted.
Yeah. Yeah, this is what we often call fitting into the noise, and we'll talk about that. Yeah, I mean, whether they're right or wrong to prefer this or that is again an interesting question, and we need to open up the sort of the general arguments. Yeah, and it may be that they are totally fools to think that's a blue line, and as they carry on, this blue line is just wonderful, and they should just follow it. It's not a curve, a box of curves fit, but yeah, but their understanding of what's going on suggests to them that that's just a curve fit, whereas that's a plausible realization of an actual geology plus the things that they know the model does wrong. Right or wrong, who's to say? Well, we can have views on this and we'll come to that. Okay, so that's the, this is interesting, even with a simple example like this, you start thinking, you know, I mean, everyone raises perfectly good questions about this. So are there general methods rather than looking at it and thinking, that makes me wonder. Okay? Fine, so I'm going to try and sort of go through this. Okay, so what I'm trying to do here, obviously, is, I mean, the differences between models and the world is as complicated a subject, or possibly more complicated, as modelling itself. Because the difference between the model and the world is everything that was too tricky to put in the model, is everything that the model left out. So the questions it raises, we are not going to address them all in this talk, but we're going to start getting tools, I hope. Okay? So I guess this is a kind of a high-level general sort of principles talk. So I guess we should start by saying what is a model. So a model basically, obviously, everything in landscape modelling, well, you know, we've seen many cases everywhere in science as cases. I mean, probably, I mean, to me, a very skeleton description that covers many, many models is that a model has, starts off with some properties of the system, and it has some rules for turning the properties of the system into the behaviour of the system. So in the geology, in this one, the properties will be the geology, the behaviour, the pressure profiles. So it's, so the properties of the system, so there's the inputs, and there's the behaviour of the system. The system gets the outputs, and there's rules, and that's a simulation. Okay? Okay? So that's fine. Okay, everything's good. So now if we think about model discrepancy, we think, how has our model oversimplified the situation? So the properties of the system for sure have been oversimplified because systems are really very complicated. We don't know what the properties are and we've boiled them down. So the properties are let's just say, I don't want to say oversimplified, they're simplified. The rules for turning the system properties into system behaviour, well, we're not sure exactly what those rules are. Even if we knew them exactly, the equations would be so complicated we couldn't solve them. And we're not applying them to the exact properties anyway, so the rules are simplified / approximated. Okay. And so that's fine. And all models have basically these features, plus maybe others. And there's nothing wrong with that. I mean, the reason that models are helpful is because they have simplified these things so that we can actually do calculations with them. And that's all good. And everything is good until the time when people forget that they did those simplifications. Okay? So so I have sat in many, many, many rooms over many, many years with many, many people. And at some point, they always say, well, the model says do this, therefore we should do this. Yeah, so it's the modeller's fallacy. What's good for people in the model is good for people in the world. Yeah, and maybe or maybe not, but it doesn't follow the fact when you build a model is a model, okay, and the world is a world. So the question about how we link what is good in the model or what is true in the model with what is true in the world is like a fundamental question. Yeah, so the issue is, here you are, you're bringing the model to a scientific journal, you're bringing the model to, I mean, it's fine to use a model, just look at it and say, this model shows this kind of behavior, that's kind of interesting, we should explore this more. So models are great for giving insight, and that's completely fine of itself. But at the point where we want to take the next step and say something about the world, then the question is, what is the claim and what is the reason for making the claim? So for using the model, so there's two questions, what is the claim and what is the reason, the rationale, as we say. So if you tell somebody, well, you should do this, yeah, then, and then something terrible happens, I mean, is it fine to say, well, I didn't say that it would work, I just said, you know, I mean, at some point you have to be clear as to what the claim is, yeah? And I'm so used to being in rooms where the model gives advice, the advice is followed, but there is no claim, so there is no notion of whether the advice was good, bad, whatever. Okay. So now let me give you my view about what the claim can be. Okay. So in my view, okay, so we start off with uncertainty about the world. Yeah. And our claim could be that having used a model for reasons that we then explain, our uncertainty has been reduced by an amount. So that would be the claim, okay? And the point about that claim is it's clear what that claim is. Okay? So I would say, you know, well, let's continue, it's semi-clear, I won't continue with this, but in fact, maybe I even have to, so it was stressed to me that we didn't want any like philosophy and stuff, we're practical people, yeah? But it's important, I think, okay, so using models reduces, or can reduce, I should say, can reduce, and I shouldn't say our uncertainty, that means a whole us, you know, the whole world, can reduce my uncertainty. About the world. Now, again, it's important here to be clear what I mean by uncertainty. In order to make the claim, I have to have like no magic words here, everything has to mean something. As a Bayesian statistician, uncertainty to me is a property of the person, not of the system. So when I say my uncertainty, I mean my uncertainty, and you, being a different person, could have a different uncertainty. It's not a property of the system, though obviously the properties of the system, if I've correctly understood them, will be reflected in my uncertainty. So this is hard for some people to understand, surely. You know, who cares what your uncertainty is? You know, isn't this what about the uncertainty? So let's just very quickly say this. Okay, so let's imagine, for example, that I flip a coin. Flip, and it lands and I put my hand on it. So I have a quick peek, I see that it's a head, I have no uncertainty. You haven't seen what's under here, so your uncertainty is you have a half each way. It's not that my uncertainty is right and your uncertainty is wrong. I mean, we can't come and say, well, you just made a mistake, that isn't your uncertainty, or it doesn't matter. I mean, my uncertainty reflects the information I have. You have different information, and that information in the broader sense can involve your analysis and etc. Yeah, okay? And so we have different information, we have done different analyses, we have different uncertainties, but that's a property of us which is informed by the world, okay? So all that I'm concerned about is my uncertainty, but now the fact that it's my uncertainty is neither here nor there, because anybody can have an opinion about anything. So what makes the uncertainty valuable is that firstly I know what it is I'm making uncertainty statements about, I have done a careful analysis, okay, and I can show you what that analysis is. Okay? So in my view, my claim should be that my uncertainty has been reduced, and my uncertainty has value because I know what the subject is about, and I have done an analysis to do this, which I can show you, and then you can look at it and see where you agree and disagree. Now, of course, it is very rare. In fact, again, I read many papers, I'm asked to review many papers, I go to many conferences. I don't know what most people mean when they use the word uncertainty. I don't think that most people actually say, which is my belief for these following reasons. If people very carefully do this, and then they try to publish, well, then most journals would actually say, well, who cares, that's just what you think. That's not science. Yeah? So, and that's an interesting question of itself. So, my feeling, in fact, is a bit stronger than this. What my claim should be, in order to make a supportable decision, is that I should reveal my uncertainty about the world for reasons that I can explain to you. And I should also, if we're now talking science, science isn't, if you like, should also talk about the different judgments that equally expert people could reach because of different views about theory and etc. Yeah. So this is like in a discussion page section at the end of a paper, they say this is what I think. Other people might disagree because of the following reasons, and it's all very chatty, and you're allowed at that point to actually confront the thing itself. But that's really where the uncertainty analysis sharpens that. It says, these are the values. Yeah. Now, either this surely has to be a consensus in the field because there's nothing here that's controversial, or that's pretty controversial. If we took, had you asked somebody else who was a follower of this different philosophy or different sort of theory, they would have reached a different argument, and that's all part of the thing. But the point is that these are our claims and our rationales. Okay? So this is what we aim to do, and so what I'm going to do is, when I talk about building model discrepancy, I mean building up my uncertainty. That's my uncertainty. Here we go. Okay? But as I said, and then hopefully sourcing it so that we can have it. And I can do this more or less carefully, and the more carefully I do it, the more value it will have. But it'll still be my uncertainty. Just like the coin, the person is half-half because he hadn't seen it. That's still his uncertainty. It's just that if only he could sort of, come around this side of the table and have a look, he would have a different uncertainty. Yeah? And so if he could come around the table and have a look, but he chose not to because he was just too busy, he has to record that and then things will follow. Anyway, sorry, this is all like a quick investment, get on and actually do something. So everyone's happy with that? Uncertainty is you? Okay? And it's fine not to take that view, but what's not fine, I think, is to say, okay, my uncertainty isn't that, it's not my judgment, it's something else, without saying what that something else is. So you're going to put your model in, you're going to say, here's my model, here's my claims, the uncertainty has been reduced, and not saying what you mean by the uncertainty. And my experience is that people don't like uncertainty being a property of a person. They would like magic uncertainty, which somehow is the uncertainty. But if you then try and pursue that and say, what could that possibly mean?
Michael,
Yeah.
so you mentioned that people have, for example, with your coin toss example, you had the peak, so you had more information than somebody else who had not seen that, so the uncertainties were different. So that was a clear example where having different amounts of information led to different subjective uncertainties. Can we, on the other hand, say that if people have exactly the same amount of information, that they should end up with the same amount of uncertainty?
Well, that raises an interesting question about what you even mean by the same amount of information. Because they have to write the same amount of information, in the sense they have to spend the same time building models, they have to have the same skill in modeling, they have to be working on the same computer. Yeah, you see that, that people legitimately can come to have different uncertainties. And none of them are wrong in the sense that they're not their uncertainties. Some people, because they're better at modelling and more skillful and are better at explaining it, may have more valuable uncertainties to report. But so the question isn't, is it your uncertainty? The question is it a well-founded uncertainty for reasons that you can explain? Yeah? So let's put a little bit of notation up. This is obviously you can see not a very mathy talk, but there will be a few things I'll sneak in. Okay, so let's have a bit of notation. So let's say X would be the inputs, and what I mean by the inputs to the simulator are the things you need to specify in order to run the simulator. So for the reservoir, it would be the permeabilities and porosities and things everywhere. For all of your examples, you know, the things you need to do, otherwise the thing won't run when you turn it on. Then f of x is the output. So that's an input vector, that's an output vector. Then there's a real world. There's y, and there's measurements, that's again a vector, and there's measurements z. So fx is trying to express what y is, z is an observation of y, it may be an observation of some part of y, usually it will. For example, if the model goes from the past to the future, you may have observations in the past but not in the future, etc.
But you don't have the real world, you only have set.
So what? No, but as we build our structure, we do view that z is an observation of something. It's just that we don't actually know. Well, I'm not saying we know what all these things are. For example, we're going to ask the question, I mean, what would be a good choice of x? It's not that, well, yeah, it's just that, that these are the ingredients for the problem. We'll see z and we won't see y, but in our modelling, we will say fx tells us about y, but we don't get to see it, we see z.
Yes.
Yeah, so it's helpful to have the notation where these things are. Yeah. Okay, so effectively, one needs to link f to y. Okay, so now I'm going to go through effectively several stages of thinking about this. Let's think about the simplest possible thing that you could do. Okay, if you could say that here's y. Okay, so let's again. This is simple. I'm not going to go and talk about this too much because I'm actually going to step back and say we should actually do better than this. But let's suppose, I mean, we're used to the notion of like model calibration, which says, you know, there's a right correct choice for x, which we're trying to find. So let's say that x, let's suppose for now that x star is the appropriate choice for x. But if I knew what x star was, then I would just run the model at that. Yeah? And the only reason I'm running it at other choices is because I don't know what the best one to run it is. Okay? So if we say the simple representation would be to say something like this. We would say that y is f evaluated at this good choice of x star, but it's not exactly because we're going to add an epsilon. Yeah? And that's going to be our model discrepancy. Now, a useful piece of notation is I like to write it like that to express the fact that epsilon and f of x star are unrelated. Okay? Okay, so that, and remember everything uncertainty is for me. So what that is expressing is a statement that if I told you that x star was the best choice and I evaluated it at that, then that wouldn't change in any way my judgments about how wrong the model was. Okay? And in fact, I mean something a bit stronger. I actually want epsilon to be unrelated to the whole function and to x star. It's just it's an amount wrong that the model is. And then of course I don't see z, I see y plus epsilon, and then that.
Michael, I'm trying to think about how model outputs can be wrong.
Yeah.
How often they are more wrong in certain.
I know, yeah, we'll get there. This is when I say this is the simplest version. Yeah, but no, absolutely, yeah. So especially I'm not going to try and convince you of this at all, but it just gives me something to start off with. Yeah.
In the bottom expression, you assume that Z has the same dimensionality of Y. Which
Oh,
is not necessarily
yeah. Okay, so let's suppose I'm not. Yeah.
For now, it's okay.
You're not
In
going to say
general,
these
that's
three
not
very
the
yeah.
case.
Okay, so Z is Y sum of Okay, yeah, no, absolutely. Yeah.
And you don't mean epsilon the same as the...
Oh, I didn't mean that, that's what neither, yeah. I certainly didn't mean those things, yeah. So epsilon would be our discrepancy, the difference between f and y. And remember, this is effectively our uncertainty about y, if we figured out x star and evaluated f of that, yeah. And this is the observational error, which again is a judgment call. Yeah? And just as a comment here to line this up with like space and time, okay, so I haven't put space and time as inputs here, and I'm not even though this is a landscaping, I haven't shown them, but you could imagine that I'm writing it like this, that y ts for a particular time in a particular space would be f, the parameters evaluated at that time point, plus epsilon ts, yeah? And so in many representations, then that epsilon would, for example, be a spatial process, it could be a Gaussian process. So in a lot of the things, if you're trying to think, patching it back to the kind of models you may be used to, yeah, then this thing has you can see has a correlation structure, but it has that correlation structure like up there. So the correlation structure will come when I specify the process. Yeah? But still in this case, the epsilon is, the whole process is independent of this whole process. Okay? And in many models, in order to keep tractability, then that's what they do. Yeah? So I think I sometimes Tony Hayden formulation. I think that as a first step, they take these two as being sort of independent, and then they nuance it a bit, but fundamentally that. Okay. So let's again be clear what would happen if we ignored this. So let's suppose this was a representation that really we should use. So if we ignored that, then it's hard to see what our claim is, because are we claiming that we think the model is perfect, or have we just not put it in? If we didn't put it in because we thought it was 0, that's fine. But if we didn't put it in because it was hard and because nobody in their field puts it in, which is too many fields that I've worked in, that is the argument that they use, okay, then you have no claim. It's not your uncertainty about the world, and it's not clear what else it is. Apart from the insight you get from evaluating the model. Your calibration will be bad. Okay? So if you try and do history matching, and you've left out the notion of the difference between the model and the world, you will history match badly. For example, if there are some choices, if there are some components which actually have quite large model discrepancies, okay, then by ignoring that, you will force out of your system ones which will probably be quite good, because they didn't get this quite one right, but you didn't expect that to be got right. So you will then take the view that your model can't do many things, which it probably could do if you thought about model discrepancy. Your forecasting will be crappy, because as you go into the future, you will have no chance of making those corrections, and so everything will be a bit wrong or very wrong, depending on the size of the things you're working on. Okay? So what I want to do a little bit, okay, so obviously how we think about these things and how we improve our thoughts, a big topic. I want to give just a few sort of handles that you can. So when I talk to people, obviously every problem is different and it's complicated, etc. But essentially, the way that I tend to like to structure it is usually the same. So I want to share how I structure this, and we'll see how far we get. Okay, so.
Cambridge has not yet got to the stage of inventing circular blackboards. Cambridge has not yet got to the stage of inventing circular blackboards.
It's a bit, yeah.
wheel is.
Oh, yeah. This takes me back to the old this is really old school where you can't quite reach the backboard. Yeah. Fine. I don't think I can even reach it. Let me come back up here.
Yeah, it's just right?
Yeah. That's for fit young people with long arms who are prepared to talk. I like this board. It's my face.
They're designed for anything other than very casual use.
Yes, that's true. You have to like a brilliant equation and put it behind glass. I understand.
Have an overhead projector there. That's what my lecturers, when I was at university, used, and then
Oh, yeah. I remember those too.
So the fundamental first, okay, obviously, there are many different ways you can structure discrepancy, and every problem has its own features. A method that I find very, very helpful is to basically say, okay, so structural discrepancy we want to know. And to basically say that there are, you divide, I mean, structural discrepancy has many, many components, but you can think of it as basically falling into two classes. What we call internal discrepancy and external discrepancy. So I want to talk about that division, okay, and get you to think, oh, maybe I could apply these sorts to my own models. Okay? So internal discrepancy. Okay? I have a computer model. It makes a bunch of assumptions. Some of those assumptions I can test by changing some features of my model and running it again. Yeah? So internal discrepancy is all the features of the model discrepancy which I can assess by doing experiments on my computer simulator. Yeah? External discrepancy is to do with all the things where I can't do that experiment because it's just too complicated, or the thing hasn't been coded to let me, or because it corresponds to missing processes. There's no experiment on the computer that I can do. Okay? So, what I say is kind of vague, but in practice it's very, very concrete. Internal discrepancy involves you doing experiments and the computer giving you answers that you can use as your discrepancy judgments. Yeah. So if you're doing that, you're doing internal discrepancy. External discrepancy is more. I mean, your internal discrepancy you have to think, but then you don't think about the numbers. You think about the ways of actually obtaining what experiments you want to do, and the computer does an evaluation that gives you them. External discrepancy is a rather more thoughtful and open-ended process. Yeah. So as a quick highlight, over many years of experience, working with modelers, they quickly understand internal discrepancy. I usually get huge buy-in on the experiments that we need to do, a lot of interest, and it's a very practical tool. So if you just take that away, then that would be great. Okay. So let's talk about internal first. It's the use of the model to test its assumptions. So, obviously, the model I said makes certain simplifications, and some of these are simplifications that you could relax in the model. Now, actually, I really would like to use a backboard. So maybe I'm supposed to do it this way. Aha! Now I can get there. I'm going to do it this way. So let's say, for example, that you have a model which maybe it's a landscape model, maybe it's a model, maybe it's something that has some parameters in it which relating to various differential equations, and maybe you've treated them as fixed over time, okay? And space or whatever, yeah? Because the thought of trying to fit the model when you let every model parameter be anything is just at any time is just too mind-blowing, yeah? However, that is a simplification, and it may be that your model will allow you to vary some of those parameters over time, okay? So you can now see there's an experiment you could do if you can access the code, which says, no, let me put a little bit of variation. Obviously, if the variation is huge, then probably that was a bad model in the first place, but let me add a little bit of variation. Maybe I have a parameter for over time for, maybe it's a flood model and it's the, how the water goes from box to box. And I have a differential equation with a rate parameter, which I just put is lambda, and I try to fit lambda. But I know that lambda changes, well, it's reasonable for me to think that lambda does change a bit over time. So I could replace my fixed lambda, I could generate maybe a Gaussian process with a small variance and a strong correlation, and I could put that in. And then I could see what happens when I ran the model. Okay. So for now, let's just think of the parameter things we could test. One, you have fixed parameters. Vary. Oh, yeah, okay, so that's actually an even simpler thing that you could do. Okay? This one you're bound to be able to do. Now, in a lot of my experience with models in principle have very large numbers of parameters, but very often people say, well, really, I'm only interested in these parameters, so I'm going to hold some other parameters fixed. Yeah? Sometimes it's done like implicitly. For example, I have a block where I know that in fact all the parameters should be a bit different, but I'm just going to put the block average, or there's a whole bunch of things which actually are not very important. So because I just need to do this, yeah, okay. So I think let me just run the model where I'm going to hold these parameters fixed. Okay. So there's a collection of parameters that just don't vary. In fact, this is in fact a good example of, in fact, yeah. Okay, so let's now say there's two things. Either for input parameters, or time dependent rates, or anything, yeah? The point is, and again, the only reason those two are different is that if it takes and recognizes an input, it can be quite easy to change it. If in fact the whole thing is programmed on the basis of a rate, you might have to get in and change the code. Okay, so, but the general notion that things that are fixed and equal, that's just an approximation, and you can run them, and you may be able to run the model varying those things. Yeah? Then state vector propagation. There we go. I mean, many models work by having a state vector, and at each time point, a state vector, there's a bunch of rules that propagate it to the next time point. And you might think, well, those rules are pretty good, but they are a bit over strict. It's not that if I actually could measure that state vector and I get it exactly right next time. So you could add, for example, a certain amount of noise, presumably a small amount of noise, because otherwise you're fundamentally criticizing the model, you're exploring those limitations. And each time you propagate the state vector, you add a bit of noise, you maybe reimpose constraints and you feed that in. So you can see that you might be able to do that with your code. You might go from, so this is a version of some of the other ones, the parameters which are homogeneous, you might set them to be heterogeneous. For example, in the age infection models, we treat certain groups of people, for example, men and women having sort of like shared infectivity rates for various things. And what it really means is that they're similar, so you could imagine sort of varying these. Often models implicitly run with a forcing function, which you put in, but you don't really know it, so maybe 4 would be forcing function. So it took me a long time when I was running one of my flood models to realize that some of the things that it was doing was assuming that it actually knew what the rainfall was, rather than, whereas clearly you could then feed in sort of, we can do an uncertainty calculation on that, and we can do this. Yeah. Then solution approximations. It could be for example, that when we run the model, in order to make it practical that we can do all the things we want, then we have to be restricted. At some point, we have to stop the iterations of the solution, possibly a bit early. Now, if we're going to do a large-scale analysis of the model, we cannot solve it exactly. Yeah? But on the other hand, to do a few experiments, maybe we can. We can take a few experiments where we can increase solution accuracy. So these are all things that you can run up the computer to do. Okay? And so what you can now imagine, this is very much linked to, the kind of sensitivity analyses that kind of I hope, that often people do anyway. But what we're going to do is we're going to wrap them up in order to get our discrepancy measure. Okay, so you could imagine, so here we take an individual possible choice of inputs, f of x, and maybe what we now do is that we think of, we're going to do a combined experiment, because what we want to know is what happens when we do all of the things that we think that we've assumed that we'd like it to break. So we will we will add uncertainty to the state vector propagation. Maybe we'll break into two groups, the homogeneous and heterogeneous. We will do some simulate sort of randomization over the forcing function. We will allow parameters to time vary. Okay? So often, because there are many different ways we can represent this, you can imagine we take a whole series of representations. Okay? So here's an experiment that we might do. So we choose inputs x. Okay? And so what we're trying to get to is that in the equation that y is f of x star plus epsilon, we're trying to get a handle on what epsilon should be. Okay? So what we say is that supposing x was the value, effectively how how much uncertainty is there about the world? When we've seen f of x, how much uncertainty should we add on? Because of course we don't actually know all these other things. It would be hard to fit them, but we can do the experiment. Okay, so we choose inputs x. Okay, then we choose n experiments. So an experiment might be so we might generate a set of random perturbations. We might generate a random forcing function on top of the forcing function we're using. We might put in a time-dependent random process to represent the slow variation of the parameters. So that would be one experiment. We can do it again, we do it again, we do it again. Okay, and then we observe f of, say f1 of x of fn of x. Yeah. Okay. So these are the different outcomes that our model would have given us had we used each of the different experiments. Okay. So now the variation in the f's, if they're basically all the same, and they're all the same at fx not doing anything, that's now telling me that, these things that I might have worried about, I was wrong to worry about, it makes virtually no difference. Typically we will have an effect. If the effect is huge, that probably redirects us back to our modelling. If the effect is there, we need to take it into account, but it's not so big that it will sort of roll over. It's probably better to actually to treat this as an uncertainty. Yeah? So you can see, for example, as long as n is reasonably big, we could maybe find the mean of that, and we could find the variance of that. If the mean of that is roughly 0, we'll say fine, there's not much bias. If it's substantially different from 0, that might make us think that there's a systematic bias as soon as we add a bit more uncertainty. And then the variance of that will tell us about effectively our uncertainty, because we've made certain simplifications that we're not carrying through the model. So you might then imagine that we calculate m of x and v of x. Okay? For example, obviously many things you can do. You can view that, if you like, as your discrepancy distribution for that choice of x. Yep. And then there are different ways you can summarize it. Notice that when we do this, of vectors, so when I casually write down that we have phi of x, what I've actually got is the covariance structure across different outputs. Yeah? So imagine, for example, the f is time point 1 and time point 2. Yeah? Then what I have is my time point 1, time point 2 in my first experiment up to time point 1, time point 2 in my last experiment. So the correlation between these is the correlation in my discrepancy between the past and the future. It's basically F1 was past and F2 was future. Yeah. So a great virtue, but a bunch of virtues of this. Firstly, that we think about the potential weaknesses of our model, and then we let the computer sort out the consequences in terms of uncertainty. And secondly, things that are normally very hard to get at. I mean, you could just about ask an expert roughly how much error there is at a particular output. Once you start thinking about covariance structures, these are really hard to think about. But this method, you get it for free. I mean, whether you're paying a price, obviously question, but on the other hand, so the question about being able to think about discrepancy here being sort of big and positive, does that have any impact on sort of downstream, or is it effectively sort of disappear? You have a way in to explore this. Okay? Fine, okay, so what we've now got is a particular choice of x, we have effectively a bias and a variance and a correlation across everything. Okay? Now, of course, we want this at every x. Okay? So it could be, so what we now do is we choose another x. Okay, so let me...
So when you said you had n experiments, what do you vary among?
So an experiment would be this. Okay, for example, okay, so I choose, okay, so a forcing function, I'm going to introduce uncertainty into that. So I take you can imagine the forcing function that I've been using, I generate a random process with mean zero perhaps, and a small variance and a strong correlation that I add on.
Sure, but then...
What I'm going to do, I'm going to run the computer
Yeah,
with that forcing function. Yeah, and I'm going to do that n times, right? I get one forcing function, I get a second forcing function.
because in effect changing x because the parameters in the forcing function are in some sense
Well,
x.
Okay, so in the way I set it up, okay, I mean, obviously this is where we're trying to describe many things, but I'm describing a situation where the way we actually are going to use the model is with a particular fixed value of the forcing function. For example, recorded rainfall or whatever. Yeah. Okay. And so the question then is, can I effectively back out saying, yeah, that's right within like 1%? Yeah. And then put that 1% back on, or do I actually have to do a much more complicated or remodeling? Yeah. And what I'm going to do is I'm going to do so. And again, for example, the state vector propagation, and I'm going to add a series of random perturbations, and then the random perturbations I'm going to get maybe n sets of random perturbations. Yeah. And I'm going to put all of these things together. I mean, I could run them individually and get some understanding of it. I mean, it could be an important thing to do. But because I'm already talking over my time, I'm just cramming these all together in order to get you a number. Yeah, okay? And the question about what you should remodel, and is obviously at any point when you think about model discrepancy, you can think, oh, that's too big, I want to remodel it. Yeah? But we're talking here about basic things that you can do which don't really require you to remodel. They just, expect they give you that external.
What do you mean remodel?
What?
Remodel, what's that?
Well, the remodel is I could now create a new model. I could say, well, I mean, if I decide that even slightly bending the forcing function gives me a totally different answer, that might make me think, oh, I need that. I've been too casual in the way I treated my forcing function. Yeah. So the notion about all of these things is partly you find, I mean, there's effects that are so small you can ignore, effects that are so big you have to confront, and there's a whole range of effects in between which it's not worth the effort. You don't ignore them because you'll be out by, but you can quantify them basically as an uncertainty statement. And the point about this, as I emphasize, is that you worry about the issues in your model, and then the model gives you back what makes sense as uncertainty judgment. Now, okay, so you did this for 1x, okay? So let's choose impact, let's call it x1. Okay, so I repeated x2. And so I'm going to get, so that will be mx1 and vx1. I get mx2 and vx2. Yep. Dot, 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 dot. To, I repeat up to xm. And I have, oh, let's call it xu. So I get mxu and vxu. Yep. And so at this point I look at them and I say, oh, well, these numbers are about the same. In which case I'm just going to use a common value, maybe. Or are they actually different? Okay. Now, if they're different, of course, I want, if you heard sort of what Victoria did, she wanted history math, she wanted to go over the whole space. Okay? So you will see m of x1, m of x2 up to m of xu, v of x1, v of x2 up to v of xu. It can be quite expensive to do, it will either be expensive or, well, it's always going to be a bit expensive doing these experiments, because you actually have to run the simulator n times to get the meaningful values for these. So what you then do is, if these are very different, you then emulate m of x and v of x. Okay? So, luckily, you'll probably use your code at that point, but instead of inputting the f's, you put in the m's. It's another expensive function. Yep. So the point. So now you have a bit of uncertainty about this thing, but again, it's like the uncertainty in the coin. Before, for some values of the coin, the flips, you've actually saw what the coin was. For other values, you haven't actually seen them, but although you've seen with uncertainty. Okay. But so this will now will go in here. Okay? So now at every choice x, you have your effectively your assessed bias and your assessed sort of and the variance on top of the bias. Okay? So sometimes people call it noising things up, but I think that you need to be systematic about this, and you need to get to this point. So my point. Sorry.
Can I just ask a question?
Yeah.
So a lot of us work with models that take order 1 hour to a week, and so we're used to smaller amounts of runs.
Let me. Okay. So I was about to discuss this. Okay. So firstly, how big does n have to be? Okay. So I mean, n has to be at least 2. Because otherwise, And after that, okay, it is then there is an inference you can make for any choice of n, which will tell you about these things. And Nathan, who did this, worked these things out in huge detail, and then he went to work at a bank. So if you can ask him to show you his calculations, he worked out. He really got a good feel for how big n had to be, and it kind of blew. He kind of mind melted a bit, but. The point is, you can do this for any n, but that wasn't going to be my point. My fundamental point here is the thing to me, the things to take away are firstly that you shouldn't feel helplessness, you can engage with it. And secondly, the following, okay, whether this is easy or hard depends a lot on how you coded your model in the first place. For example, state vector propagation. It could be that your model actually goes blah, 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 here's a state vector, here's something that happens to it, and then blah, 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 okay? And in a very transparent way, you can get in, and you can then, you can modify the state vector and propagate. It could be that you think, wait, even though I could do it that way, that's not computationally very efficient. I can kind of do it on the fly whatever actually by clever tricks, which will actually make my simulation a bit faster, but I never actually constructing a state vector, at which point you cannot do that experiment. So the notion, or if I'm varying my parameters, okay, over time, I can either make that quite simple because of a fairly transparent coding, or it could be like God's own test of humanity just to get in the code. Yep. So your code. So when you build your model, okay, my strong advice is that you think about the assumptions that you're making and how you are going to test them, and how your code gives you access so that you can do those tests. So just like the subject of experimental design, when people do experiments, we advise them to talk to a statistician first, so that their experiments can then be analysed. Yeah? When you build models, if you're actually trying to bring them to application, think about what you're going to do and think therefore about how you're going to build these things out. So to continue, for example, your question, if your model takes a very long time to run, maybe what you need is to have a faster approximate version of that you also build, so that you can start doing these experiments on the fast version, and then you can do, which you can do quite a lot of, and then when you can take them to the small model, to do the slow version, you do a small number of those, you get the relation between the fast and the slow, and you can do something. Yeah? Now, of course, getting a fast and a slow version is good anyway. After all, if you want to build emulators at all, I mean, if your model is slow, all the magic about building emulators is even more important because it's slow, but it's even harder to do. But you want to have a multi-level version, so you run your model many times to build fast, approximate emulators, which act as priors to tune onto your slow system. Okay? So if your aim is to do something useful in the world and to get understanding of the world, okay, you should start in your model specification, especially by thinking about the right ways to build models that will help you to do that. And that's probably almost the most important thing I can say, apart from the fact that you should do this and you should get a hold of this, is that you know, it's not actually too late when the model's produced, but it's much, much, much better to think actively about, you know, how you would like to use a model to learn about its own deficiencies. Now, I'm conscious we've now reached 11 o'clock and I haven't talked about external discrepancy yet. Does anybody else have any questions about this? I mean, I do recommend, my experience is that this is a good thing to do, and once you start getting into it, you actually find useful things out of it, and it's easy to explain what it is that you did, and if journals can understand what you did as well, because it's a operational thing. Yeah.
Just in my experience with modeling, it's often the feedback structure that is assumptions about feedbacks that are the most critical assumptions. So where ultimately some part of the model feeds back to another part of the tool itself. Would that be assumptions about feedbacks, for example, taking them out or strengthening them? Would you see that as exploration of the internal discrepancy or external?
Well, my kind of trivial answer is, if you're getting a computer to do the analysis, it's an internal. So imagine that, for example, if the strength is a parameter, yeah. Now there's two sides to it, because you're trying to fit that parameter anyway. But it's if your notion is that parameter has like a fixed value, yeah, and however you run it, you're going to end up estimating that fixed value. But really, you know that feedback is kind of slightly slowly varying over time or whatever, yeah. And so you've ignored that. Then thinking about the variation in there, there are experiments you could do that would be internal. If you entirely want to change the feedback loops, then I would think that that would be either a second model or it would be external discrepancy. So anyway, so as I said, I mean, I can talk, I mean, I have got stuff to talk about external discrepancy.
So I'm going to suggest that we go for coffee now and then come back and do external.
Yeah, I could be like the second speaker.
Because we didn't have a second speaker.
Yeah.
So so we'll pause on the cliffhanger of external discrepancy to come, and we'll have coffee, and then I'll just gather everyone at the table. Yeah. We've had a break.
I thought about whether, since it's Friday and different people will be here next week, whether we could recap what we've kind of done this week.
Also different, I see.
After coffee.
Well,
that's a good idea.
We should go with we should try both. So let's see how the second talk goes.
Yeah. It won't be. No, I haven't got. Yeah, I mean, I have got some slightly puzzling statements to make about external discrepancy, but they weren't taken out.
Yeah. Well, let's do puzzling statements and then just open it up for discussion, and then we can go that way.
That's a good idea.
Yeah, that's a very good idea.
Who's not here next week then? Just to
Who's not here next week?
not here.
Me, I'm gone. This is my last day.
Right.
now either. So. Let me just pause.
Peter said